This is question 3 of 5th book, Radioactivity Toy Time 1. It's a question that starts by showing this grid where we've got a plot of the number of neutrons against the number of protons for various different isotopes. So you can see it labels some as unstable and one at the end as stable isotopes. And the first question is, what is an isotope? So when we look at the chart, you can see we've got two versions of polonium, both with a proton number of 84, but one having a mass number of 214, one having a mass number of 210. Also for lead, two versions, both have a proton number of 82. One has a mass number of 206 and one has a mass number of 210. So hopefully this is a helpful reminder about what an isotope is. It's about having the two versions of an element with the same number of protons, but with different numbers of neutrons. Because of this, we can express it in lots of different ways. We might talk about them having the same atomic number. We might talk about them having different mass numbers. But I think same number of protons, different number of neutrons is about as clear as we can be. Why are some isotopes described as stable? So this is about whether they're going to undergo radioactive decay or not. The unstable isotopes are ones that will radioactively decay into something else, whereas the stable isotope stays as it is. So a stable isotope is one that doesn't undergo radioactive decay. B part 1, use the grid to calculate the number of neutrons in a 210 polonium nucleus. So that's this one here. In terms of using the grid, the only part we need is that it's got a proton number of 84. So once we've got to this stage, we could write down the polonium atom like this with a 210 and an 84. We remember that this at the top is the number of protons plus neutrons. This at the bottom, the atomic number, is the number of protons. So the difference between those is 126. Describe what happens to the number of protons and the number of neutrons when a nucleus of 210 lead decays to form 210 bismuth. Let's throw about this now because it's not relevant. So we're looking at this section here, going from 210 lead to 210 bismuth. If we want to read it off the chart, we can see that the number of neutrons has decreased by 1, and the number of protons has increased by 1 as we go across from one to the other. So if we're describing the difference, describe what happens to the number of protons and the number of neutrons, we're going to say the neutrons go down by 1, and the protons increase by 1. I think when we learn about this, we sometimes say a neutron turns into a proton. I don't think that would be a good answer here because it asks you to describe what happens to the number of protons and the number of neutrons. So I think really we should do the two separately. State what type of decay occurs. So hopefully you remember that when a neutron turns into a proton, this is a form of beta decay. This is beta minus decay. Symbol is always good, but if we want to write it, we can. Even better if we were to write beta minus. But if you just write beta, it's assumed it's beta minus. And for C, explain why the mass or nucleon number and the atomic proton number do not change when a gamma ray is emitted from a nucleus. So to answer this question, I think there's two aspects of it. We want to describe what about the gamma ray makes this true and what doesn't change in the nucleus. So the idea that the gamma ray is a form of electromagnetic radiation. It's not formed of particles, it's formed of an electromagnetic wave. And secondly, that as a result, the constituent parts of the nucleus do not change. So the number of neutrons and the number of protons are unaffected by emitting the gamma ray, and therefore the nucleus, the atomic and nucleon number do not change. I think you get a mark for that second part because it doesn't say the neutron number and proton number, because it says nucleon number. I think we're well within our rights in answering this question to talk about the number of neutrons.